The first time I ever got the idea that I might be able to own a personal computer was in 1975, I believe it was, when Popular Electronics displayed the Altair 8800 microcomputer on its cover. It was far too expensive for me to afford at that time, but only a little bit more than a year later, in August of 1976, the same magazine showed the build article for the Cosmac Elf microcomputer, a much less capable computer than the Altair, but still quite useful as an educational tool and theoretically expandable into a more useful machine. I never did build one of these things during my youth or during most of my career, but as I become more interested again in vintage microcomputers, I've decided to do a new build of the original Cosmac Elf, trying to stay as close as I possibly can to the original design and appearance, and trying to build a museum quality example, keeping the quality high as much as I'm able to. This video is basically a slideshow of all the steps I went through to build my Elf, and at the end there is a brief video showing it in operation. The first thing that I did was to take the original magazine article's dimensions for the wooden rails onto which the Elf's perf board and toggle switch board would rest and hold everything together, and cut those out. I had some maple wood left over from the display case I was building for my Heathkit project, which I also have documented here on YouTube. And at the same time I was building that, I was building the rails to actually build up to 2 of these Elves if I decided to make one for somebody else. And so I cut them out in the right dimensions, stained them, and varnished them. The original article's instructions for building the toggle switch panel was to just take a piece of aluminum, paint it black, and use dry transfer lettering. I decided to do it a little better than that, and I was also planning at the same time to try out a service I'd found called Front Panel Express in Seattle, Washington, that'll make low-volume custom panels of very high quality. And so I combined my desire to test them out with using this project as a trial balloon, I guess. And I downloaded their free software, set up the dimensions of the panel according to the instructions in the original article. I put in the 2 mounting holes on the side, again scaling up the photos of the original. I placed the 8 holes for the main row of toggle switches, and 4 more holes for 3 more toggle switches and the input push button. And I also utilized the fact that Front Panel Express will also do blind holes, which are drilled in but don't go all the way through, and those are on the back of the panel. I found out from C&K, which is the company I was buying my switches from, they had anti-rotation rings with a little tab that would go into a blind hole in the panel. So I figured out the dimensions and locations of those and placed those on the Front Panel Express panel designer. And then, of course, placed all the text, trying to get the font and the location and the size and everything exactly like the original. With the design complete, I went ahead and placed the order directly with Front Panel Express from their software, and while I was waiting for the approximately 1 week it would take to receive my panels, I proceeded with more of the design. I obtained a sheet of vector board slightly larger than the size required by the original plans, and cut it down to the required 4.5 inches by 5.5 inches. And then drilled holes in positions appropriate from scaled photographs of the original, and at a point where they would fit the rails properly. And then I drilled holes in the rails to match up with the perf board, mounted the perf board to the rails, and then took a scale printout on my laser printer from the Front Panel Express panel design software, and used it as a template for locating and drilling the holes to mount the toggle switch panels once they arrived in a few days. Next up was making the heat sink for the voltage regulator. I used a piece of 1/8 inch thick aluminum I got from the hardware store and cut it out in the sizes based on scaling the original photographs. And I should note that much of the scaling came from views of the original, and you can count the holes in the perf board and use it as a means of scaling all other dimensions and locations, because the holes are on a 0.1 inch center. So it's almost like having a piece of graph paper over the assembly. And then I wire brushed the cutout pieces for best appearance, test located the voltage regulator, drilled the holes in the heatsink and the perf board, and mounted the regulator to the heatsink and the perf board as shown here. There were several parts that I was going to have to get from other places, but most of the parts for this build came from DigiKey and were all new parts. I had to buy the 2101 RAM chips, which are only a 256 by 4 RAM, and so you need actually two of them to make a 8-bit wide word of 256 words. And those came from Jameco Electronics. They don't sell the 2101 RAM chips, but they do sell the pin-compatible 5101 RAM chips, which is just the CMOS version. Everything else is identical, and they can be used in place of the 2101s. For the crystal oscillator, I could not find the required 1 megahertz crystal in the size and appearance that the original had. The new ones are so much smaller and usually in a different shape. So I had some old crystals of a different frequency but the right size, and I stripped off the plastic outer wrap so it wouldn't show that they were the wrong crystal, and also since the original shown in the photos didn't have a plastic wrap. So I was going to use this as a facade and put the real crystal down underneath the perf board. And I bought all the wire wrap sockets from DigiKey. And then the remaining things to do were to come up with the 1802 microprocessors, which I didn't find anybody selling new, but at least not through regular distributors. The best source for those seems to be eBay. There are a number of sellers selling new 1802 chips, and I bought a couple from a seller there. And then the final thing was to get the dot matrix style decoded LED displays, and you could use a couple different kinds with the original. There was a Hewlett-Packard part, and there was also a Texas Instruments part that were basically identical in appearance. The main difference was the pinout. I chose to use the Texas Instruments version, which is the TIL311, and there are a number of people selling reconditioned ones on eBay, but I often use a company in China called JotronElectronics.com. They sell a lot of new old stock electronics, and I've found them to be a reliable source for projects when I have to replace some old chip that's hard to find otherwise. They almost always come through with brand new parts. And so, sure enough, they gave me several TIL 311s for this project. And just to verify that they were working and that I understood how they worked and had the right pinout, I built a little test fixture and quickly went through all the hexadecimal possibilities from 0 to F as shown in this sequence. Next up, I mounted all the other parts on the perf board, again using the grid of the perf board holes to match the same grid from the photos of the original, so I was sure I had everything in the same positions. And I used some Vector brand single pin wire wrap sockets that just have a little cradle on the top where you can solder a single lead from a component, and I use those for mounting all the discrete components. And then after I'd done that, I wanted to build a rear panel for the Elf. There weren't any photos of this on the original, but there was implied that there was some sort of a rear panel to hold a socket for the incoming power supply. So I used some scrap 16th inch thick aluminum that I had laying around. I'd already drilled it for something else, but I found a way to lay it out that I could not interfere with, or at least reuse some of the existing holes. And I drilled those out to match the power jack that I'd selected for my power supply. And I also wanted to add an audio output. This was a small deviation from the original, which did not suggest an audio output, but almost every build I've seen or heard of had one. They just tied it into the Q line that normally drove the single LED, and by doing so you could monitor it through a speaker or an amplifier in a speaker and listen to tones as long as they were in the audio range. Almost exactly 1 week after I placed the order, Front Panel Express delivered the 2 completed panels that I'd ordered, one for the primary and one for the second one I was thinking of building. And you can see here a front and rear view. The front view obviously has the engraved and paint-filled lettering, and the rear view shows the blank or dead holes that are drilled partially through from the rear to hold the anti-rotation pins of the switches. And then I laid it out to mount it on the rails and drilled the holes in the rails. Next up was to mount the switches. I almost always use C&K brand switches, and I buy them from DigiKey. I found some that were an exact match of the originals, although the original article didn't specify an exact model number. It just said toggle switches. But they come in, micro size and mini size and full size families, and it was clear that one size family was going to be the only one that had the fit and look of the originals. So I selected those. The model number is shown here. Then I had to figure out the proper depth to set the back nut on the switch so that it would go the proper depth in the panel that I had ordered from Front Panel Express. And so I did a couple experiments to make sure everything was going to line up and go the proper depth, have the proper appearance. And then I set all switches up according to that and then mounted them. And you can see there are views here of the anti-rotation rings going into the blank holes in the back of the panel. I also selected an appropriate matching momentary push-button switch from C&K and mounted that along with the other toggle switches, and the push button's only used for the so-called in function, which is used to input data that's been selected on the other toggle switches. Along with the switches, I had also selected the color cap for the push button switch in the proper style and color to match the original, and also the original had color caps both in white and red over all the toggle switches, and so I obtained the proper C&K color caps and installed those on the toggle switches as shown here. It became apparent that for assembly and wiring of the rest of the computer, I was going to need something to hold it in position at a good angle to work on, especially for the wire wrapping. And so I threw together kind of a crude angled support for it. I had in the back of my mind that eventually I might clean this up a little bit and use it for display purposes, but I just used, rough plywood. I didn't try to use nice hardwoods or anything for this. But the design is quite simple. It's just held together with epoxy. I put felt pads on the bottom and little rubber bumpers on the top so it wouldn't scratch up the Elf itself when I was working on it. And you can see the results here, both with the Elf front side out and front side down. Many of the original Elf projects were audio tone generators, and the programs are a little more complicated when you do those because the processor's fast enough that the tones generated from a simple program will be too high in pitch and not really be in the audio range, so you have to build in time delays into the programs to keep it in the audio range. And I learned from Lee Hart's 1802 membership card, which is sort of a hybrid Elf construction kit, that on his he used a ceramic resonator instead of a crystal, and he kept the frequency in the high kilohertz range instead of the megahertz range, and using a trim pod it could be throttled down to a very low speed. And I thought the flexibility of the clock speed might be useful in this build, but I didn't want it to be obvious that it was there. And so I actually bought a prepackaged hybrid 1 megahertz oscillator package, and also the components such as the ceramic resonator and the trim pot and a Schottky inverter package for the low frequency oscillator, and built those onto a small piece of perf board. There wasn't room to use wire wrap on it, so I used wire wrap wire and just did little solder tack jobs, rather crudely I have to admit, and wired it up so it would fit in an empty space right below where the facade crystal and its support components would be on the top of the perf board. And you can see here that I'm testing it out using an external power supply. First, I've got the jumper on the small board set to nothing, and the scope shows that there's just a 0-volt output. And then I have the jumper selected to the low frequency oscillator, and there are 3 scope traces here showing from the lowest frequency up through sort of a medium frequency and up to the highest frequency it can generate. And then finally I move the jumper over to the other position, and now I'm engaging the hybrid 1 megahertz oscillator package with its output at, of course, 1 megahertz. And normally I would have this selected to the 1 megahertz because it matches the original Elf, but if I ever wanted to, I could move the jumper over and now be running with a much lower clock speed, trim pod adjustable. Next up was to arrange the power supply. I usually use the CUI brand wall warts, little switching power supply wall warts, and I selected one with a 9-volt output, and I think it was good for up to 1 amp, and that's shown here. And of course its output plug matches the socket I'd put on the rear panel of the Elf. And to help keep the heatsink from running quite so hot, I used a couple of diodes in series between the power jack and the input of the voltage regulator, and that each of those drops 0.7 volts each, so that's a little bit less that the regulator has to drop, and therefore it wouldn't run quite so hot. And I deliberately wired up the connections with longer than necessary pieces of bare bus wire. It's actually just, I think, 22 gauge solid tinned wire with the insulation stripped off. But I decided that I wanted to use my power distribution to all the ICs and other components in a star configuration. So instead of just daisy chaining them all in a single long line of ground and plus 5 volts, I would wire most components directly back to these power buses near the regulator, and that would help me avoid noise on the power supply. And I don't really think this Elf design really needs decoupling capacitors. It's all CMOS, so there's very little power glitches anyway being generated. If it was a bigger design, I would have used decoupling caps, but it wasn't called for in the original. I didn't want to put them on mine for that reason. And I thought, you know, good power supply distribution can't hurt, so I did it that way. And that's why you see the power supply layout the way it is. Another thing I've learned from doing wire wrap on other projects in the past is that it can be really hard to keep track of which pins are which when you're looking at the wrong side of the board or the back side. Everything's reversed, and you end up having to count all the pins in reverse every time you land a wire, and it can increase the chances of making mistakes significantly and increase the time it takes to do the work. It just makes it much more of a hassle. Wire wrapping is tedious enough without that kind of thing being added to it to make it worse. So the usual solution is to use little labels affixed to the back of the perf board that show the pinouts with the correct reversal. And you can buy those, but these days the few places that have them sell them in packs of like 1,000, and the cost is quite high. I didn't want to go that route. I'd have a bunch left over I could never use. So I was thinking, what software do I have where I can design these myself? And I realized that the Front Panel Express software is ideal for this. It allows high precision location of shapes and letters, and you can print them out to scale on your laser printer or whatever you have. And so I decided to use that software for this purpose, and these pictures coming up show the steps I went through to do that. First, I tried to pick a color that was more or less the same color as the perf board, and I laid out a rectangle that would fit between the pins of an IC without quite touching it. I didn't want it to get in the way or actually be touching the pins. And then I found a good size of number that would fit and laid them out using the XY coordinate feature of the software so I could precisely position them instead of just dragging them into position roughly. And I could print it out on my laser printer, and I did a test and realized that the way I did it, the numbers were all right side up, but when you actually put it on the board, everything was reversed from what I actually wanted it to be and the orientation of the ICs I had. So I flipped all the numbers upside down and reprinted them, and I did a design for the 14-pin dips, the 16-pin dips, the 22-pin dip, which has a wider spacing between the rows, and that's for the memory chips, and finally the 40-pin dip for the microprocessor. And with those designed, I printed out. Unfortunately, the the front panel design software only allows you to print one image per sheet of paper, so I could not tile them. So I kind of wasted some paper here, but it's not that bad. And I printed one out on a sheet, cut it out to a size closer, but still manageable. I used some permanent adhesive of the kind I usually use to mount other kinds of labels to things, and then cut it out to the exact size. I used a set of needle nose pliers to position the label, and then pressed it down with the back side of my wire wrapping tool to make sure it was fully adhered to the board, and repeated this for all the other ICs. And then I realized that I had forgotten to put the IC numbers on the label designs as I did them. That would have been a nice thing to do. It's nice to know not only the pin numbers, but which IC you're looking at when you're wire wrapping. And so I just drew those on with a Sharpie pen. I didn't do the greatest job, but at least it worked. And you can see the final result here, that everything is labeled, and this will make the wire wrapping much easier. So the next step then was to get ready for the wire wrapping process, and I bought 4 new rolls of wire wrapping wire. And wire wrapping wire is a 30 gauge solid tinned wire with a Kynar insulation, and I bought it in these rolls as you can see here. I think you can make out the part numbers on them if you wanted to order the same thing. It's what used to be OK Industries, but it's been taken over by Jonard Tools, so it's a subsidiary of them. So some of these rolls are labeled OK, they're older stock, and some are labeled Jonard. And I also had always in the past just had the rolls laying loose, but the wire tends to get kinked and twisted. So I built a quick little stand to put the spools on so they would be held in a better position, and you can see that here. So now that everything was put in place, it was time to actually start the wire wrapping. stepping back for a moment, before I even started this build, I had to develop a working schematic. And the original magazine article had a good schematic in it, although there were some wires shown that weren't really needed, and just the way it was shown wasn't the clearest in some ways. And I also wanted to learn something from this, so I studied it in considerable detail, and also bought on eBay the original 1802 microprocessor manual and read up on that, make sure I understood what all the signals did on the processor and how they worked and interacted with each other. And also I reviewed online a couple of other schematics of commercial versions of the Elf that were made, in kit form, for example. That often happened with these popular electronics magazines, that somebody would immediately come out and make a kit version of it to help readers of the magazine build the projects more readily than if they had to go out and do everything themselves. And I was just sort of comparing notes and seeing if I could detect any problems with the circuit. Sometimes these magazine articles have errors in the schematics and so on, and I wanted to make sure I had all that figured out before I started the build. And you can see here is my hand-drawn schematic for the circuit, and I had marked it up extensively, but this is what I worked from. And then starting out, I started out with the black wire, and I was doing the ground bus, or the negative supply rail, if you will, and wired that up. Again, I didn't want to use a daisy chain so much as I wanted to use a star topology, so I would wire a couple of chips that were in a row in a daisy chain and then bring them back to the ground bus, and then wire the next row's grounds back to the ground bus and keep working my way down. In the case of the microprocessor, I gave it its own wire back to ground. In the case of the high current consumption display modules, I gave each of them their own wire back to ground. And then I did the same thing using red wire for all the V pluses, or the plus 5 volt supply rail, using the same topology. At that point, I ran bus bar to the toggle switches and the push button switch, and then connected those bus bars up to the plus 5 volt power bus and the ground power bus. And then I used, well, before I really got into doing the control wiring, I took the opportunity to wire up the audio output jack, and I used a 10 microfarad electrolytic capacitor, and I want to say it was a 10K resistor or something in that neighborhood. I took the output of the Q output of the microprocessor, which normally drives the Q LED on the front of the perf board, and I also had it go through another buffer. I just used one of the spares on the Schottky inverter chip that I was otherwise using for the low frequency clock oscillator on the small secondary board, and I went through that to act as a buffer, and then ran through the electrolytic capacitor in series, and then used the 10K or thereabouts resistor to ground, and this formed a simple RC level shifter, removing the DC component. So instead of a 0 to 5 volt signal, it would be a signal centered on 0 volts that would go both plus and minus, and then finally wire that up to both the left and right channel pins of the stereo phone jack that I had put on the rear panel, and this was set up so you could plug in a set of stereo computer speakers of the self-powered kind and be able to drive it that way. Anyway, so with that out of the way, I went on with the white wires and used that for all the control signals. Anything that wasn't actually data or address was done with white wires, and that's really about half the wiring. And then I went on and added, using blue wire, I did all the address lines, which in this circuit go only to the RAM or memory chips, They're not decoded for anything else, and it's only the lowest order 8 bits because it's only working with 256 bytes of memory. So the upper 8 bits, the higher order 8 bits, aren't even connected to anything on the processor. And then finally, using the blue wires, I wired out from the 8 data lines on the processor to the RAM memory chips, to the buffers for the display drivers, and then from the outputs of the buffers onto the displays. And also I went to the well, they're not actually inverters or buffers, they're electronic switches, and there's 2 ICs for that, and that's what couples the 8 toggle switches for data into the data bus when required. And so those got wired up as well, and then of course the inputs to those switches got wired up to the 8 toggle switches. With all the wiring done, I went through and did a thorough continuity check based on the schematic to make sure I had in fact wired everything up and to the correct pins. This time I'm looking at it from the front, so it's a double check to make sure I haven't reversed anything. And for good measure, I usually tapped the adjacent pins on either side of the pin I was looking for to catch any shorts to adjacent pins that might have occurred due to sloppy wire wrapping. And then, of course, you can see here the front of the nearly finished Elf without the chips plugged in, and then with the chips plugged in. And then the moment of truth when I plugged in the power supply and the displays lit up. But of course, this isn't proof that anything is working because those are sort of autonomous. And the only proof that it's working is to actually put a program in and test it to make sure that it's running. The first program that I put in was a simple one from the actual magazine article, and it simply flashes the Q LED on and off at a moderately slow rate. These couple of pictures show that program in operation, one with the LED turned on at the moment and one with it turned off. Alright, so here's a demonstration of the Elf in operation. I'm using this program here, which is the slow blink program from the original Popular Electronics magazine. I don't know what it is, it's like 2, 4, 6, 8, 10, 12, it's 13 bytes long, and I put an extra 0 at the end, which doesn't count. The program ends with the 0, 1. That's in hexadecimal. The program is entered on these 8 toggle switches in binary, although the color caps help break it up into 2 4-bit words or nibbles, and that helps you figure out the hexadecimal because you're just dealing with 4 bits at a time. Now there's the input button here, which is a momentary button, and when in load mode, pushing that momentarily clocks in whatever's on the toggle switches into the processor. It goes into a register in the processor. Then the processor automatically, because it's in load mode, it automatically writes that out to whatever memory location in the RAM is currently pointed to by the program counter, and as soon as it's done that, it keeps that data on the bus, on the data bus that is, and increments the program counter. And so then you can change what's on the toggle switches, push the button again, it sucks that data from the toggle switches into the register in the processor, writes it out to the new location in memory pointed to by the program counter, increments the program counter again, and keeps doing that. So that's sort of a built-in DMA function, or direct memory access function, built into the 1802, and it helps you do these rudimentary program entries. And if you do the same thing but turn memory protect on so the memory can't be changed, the processor is still trying to do the same thing, but it can't because the memory is protected. That allows you to go through the program and inspect it to see what the program actually is without changing anything. So that's what the MP button is for, or toggle switch. If the MP switches up, memory is protected, cannot be changed. If it's down, then it can be changed. For most programs, you'd want this to be in the up position unless the program by design is supposed to change some memory locations. So the other two switches are the load switch and the run switch. And the way that works, I've got a little diagram here. When both load and run are turned off, or in the down position, the processor is cleared and the program counter is reset to 0000 binary, or hexadecimal actually. If you turn the load switch on while leaving the run switch off, it puts it in load mode or memory review mode if the memory protect is on. If you turn the load switch off but turn the run switch on, then the processor's in run mode and it runs whatever program is in there. If you turn both switches on, then the processor remains in run mode, but it goes into a wait condition where everything is kept exactly where it was while running, except it doesn't actually advance with execution of the program. It just stops exactly where it was, everything in stasis. And then when you relieve the load switch back to its 0 position, you're back to this state, then it resumes running. So it's a pretty logical layout, pretty easy to understand, and I'm going to go through and enter this program now. Try to reposition this so everything shows up. Hopefully the display is visible. So nothing has been written to the LEDs yet, and they automatically, because they're autonomous hybrid chips, they automatically display 0 because nothing's been written to them. That is not an indication that there is 0 in any particular location in memory or that the switches are at 0 or anything. It just powers up that way. So here's how I'm going to go about entering this program. I have to make sure it's not in run, make sure memory is not protected, and then I have to put it in load mode. Now, because load and run are both off, the processor is reset and the program counter is reset. So I'm starting out with the address of 0000 at this point. As soon as I put it in load mode, it's now receptive to entering the data on the toggle switches into memory in an incremental fashion. So the first thing I have to do is toggle in 7A. That's 7 in the upper byte, and A is 1010, so that's the pattern for 7A. And when I push the in button, you can see now that the processor's brought in that data from the toggle switches, brought it into the processor, saved it in the first memory location, and the data remains latched in on the display. Even if the data bus changed at this point, the display would still read 7A because that was the last thing that was on the data bus when the processor toggled the strobe on these displays. So the program counter has automatically been incremented now because I'm in load mode. So the next thing to do is F8, and F is everything turned on the first order, and only the highest order bit here. This is the 8 weighted bit, so that's F8, and F8 is displayed. Next it's 10, so I turn that to 1, 0, enter that, and verified 10. B, which is 1011 in the higher order, and 1 down here, that's B1. Enter B1, and then 21, that's this, 21, 91, 8, 9, and 1. 9's been entered. 3A, so this is 3, and A is this pattern. 3A, 0, 4, 3, 1, 0, 0, 7B, 7B, 3, 0 again, 3, 0, and finally 0, 1. 0, 1. And I always like to put an extra byte in at the end, that's 0, 0, so I do that. So now I'm going to take the program or the ELF out of program mode by taking the load back to 0. This also resets the program counter and the processor. Now I'm going to put memory protect on so I can't inadvertently change memory. And I'm going to return it to load mode, but instead of toggling in information, I'm just going to keep pushing the in button and verify that my program is what I think it is. 7A, good. F8, 10, B1, 21, 91, 3A, 04, 31, 00, 7B, 30, 01, and my 00. After that, I don't know what's in there. Probably some random garbage. Right now it's mostly zeros. Very good. So I take it out of load mode again. I leave my memory protect on because this program does not need to change memory. And then all I need to do is put it into run mode. And there you can see that it's flashing the Q LED on and off at a moderately slow rate. So that's the basic operation of the ELF. Now, in theory, the 8 toggle switches here can be treated like an 8-bit input port, and the display can be treated like an 8-bit output port, displayed in hexadecimal. So I could do little programs here that read data from these switches and do some calculation or logic on them and display the results on the 2 digits here, or in some way affect the Q output. I can generate tones or other serial data signals out of the jack on the back using the Q output for that purpose. I can write programs that do some basic math, although there aren't really enough controls here to say I specify an A operand, a B operand, a C operand independently. The most practical way of doing that is to actually enter them as part of the program. Perhaps at the end of the program put in your different operands and just have them in memory, then run the program. It knows to look in those locations for the data. It does the calculation and it stores the result in another memory location. Then I come into load mode and sequence through until I'm at that memory location and see what's there, and that would be the answer. So with just what's here, that's pretty much the limitation of what can be done. Obviously, additional chips can be added on other boards and wired in, but the original intention of the ELF was just to provide a really basic trainer, and that's what we have here. I've never really had much enthusiasm for the gussied up versions of the ELF. They're marginally useful. I think the charm on the ELF is this original configuration. Joe Weisbecker, who was the inventor of the 1802 microprocessor at RCA, was also the designer of the original ELF and wrote the articles that went along with it. And if anybody knew the chip, he knew its ins and outs and the tricks you could play with it, and he took advantage of those in the design of the ELF to minimize the parts count and still have a basically useful demonstration computer. So one more thing I can demonstrate. I can take this out of run and you can see that the Q LED stopped running. I can resume running and it picks up where it left off. I can, as I pointed out before, if run is on and I turn load on, it stays in run mode, but it puts the processor in a wait state. But everything else is left exactly where it is. All the internal registers and everything are exactly where they left off. By taking the load switch down, it picks up exactly where it left off. And it's possible for me here to try to demonstrate that by trapping this. I put it in a wait state here, and now I've trapped it with the Q LED on and a 91 on the data bus. Now the 91 stays because it's latched or strobed in, but the data bus is obviously changing, you know, at a fairly high rate of speed as the program runs. I can put it in wait again, and I've caught the LED on. Wait again, now I caught the LED off. Anyway, so that's a basic demonstration of the Elf in operation.